What if AI and an emerging new technology called quantum science could save millions of lives every year from diseases like cancer or pneumonia? Hello, you're listening to Where What If Becomes What's Next from Carnegie Mellon University, where we ask the bold questions that become innovations for the betterment of humanity. I'm your host, Randy Scott, and in this second installment of our two-parter on healing with intelligence, we're exploring how AI and quantum science are transforming healthcare by driving innovation in patient care and diagnostics and accelerating the accuracy and speed of detecting diseases. Early diagnosis of pneumonia is crucial in saving lives. The disease has been a leading cause of death in the United States and globally for decades, but it's a preventable disease. The problem is, healthcare systems face challenges in diagnosing it. Detecting it usually requires chest x-rays or blood work, plus the radiologists and nurses to administer tests and analyze results. That's where quantum science, AI, and machine learning come in. Algorithms that can deliver reliable diagnoses are transforming healthcare, and these models have the potential to save millions of lives by providing faster answers and faster access to care for people around the world. Sridhar Tayur is the Ford Distinguished Research Chair and University Professor of Operations Management at Carnegie Mellon University's Tepper School of Business. He is also an expert on quantum science and how big data and AI can better diagnose diseases like pneumonia.
This is a very preventable thing if people are able to take the image and quickly figure out, do you have it or not? If you don't have it, you say, okay, that's not your problem. We'll deal with it. But if we have it, hey, let's send this person to the treatment earlier. So I think the ability to take images, send it information out, and have a fast algorithm which can tell you, do you have it or not, I think can be put to good social good. And that was another reason really to see, how to use this technology really for the social good.
Before we start talking about quantum science in healthcare, and specifically your project in diagnosing and treating pneumonia, let's explain it more generally first. We've heard a lot about machine learning and AI. Now we have this new fantastic quantum technology. What's the difference between quantum and AI and machine learning?
So first, we're talking about two different things entirely in the following sense. Quantum is not competing against machine learning. Quantum is simply an alternative to digital computing. Okay, so that's one thing. So people then ask, what's the difference between a quantum technology and digital technology? The example I give is just like a fighter jet is not a faster Ferrari because it works on a different principle. That principle requires wings and it actually takes off. Quantum computing is not faster digital computing. It actually works on a different physics principle entirely. Quantum computing can take you from A to B, but today we know that classical computing or the digital computing cannot take you from A to B. So what do you want to do with the quantum? We want to do machine learning. So hopefully that clarifies that quantum should not be considered a competitor to AI or ML. It is simply the hardware on which we will do AI and ML.
That's a really interesting distinction. Okay, we understand where quantum fits. Now, how do you see quantum technology being used in healthcare today?
Within the healthcare world today, it is doing things faster. We can do the same thing with digital machines. It just takes longer. So today, I'm using a fighter jet just to go faster than a Ferrari, but not actually taking off that much.
There have been some mind-boggling estimates about how fast quantum computing is in comparison to supercomputers. And I mean supercomputers taking hundreds of thousands, even trillions of years to accomplish a task that a quantum computer could do in a few hours. So when you talk about faster, we're potentially talking about faster than all of time.
That is correct. So the problems we're studying in healthcare are hard problems, but they are not problems that are undoable on a classical computer today. It just takes many days. On a real quantum machine, it might start taking minutes.
Let's talk about a problem you're turning to quantum computers for, pneumonia diagnosis, which comes primarily from analyzing chest x-rays and CT scans. AI models have to be trained, and that process can be very time-consuming. Is that where the speed of quantum comes in on this project? It's helping to train machines to detect pneumonia faster?
Right. So what we did was we took thousands of images that have already been trained on classical machines using well-known machine learning algorithms. We know how long it took and what is the quality of the solution with respect to how many false positives it gets, how many false negatives it gets, what is its accuracy, and so on. We know that. So it's a benchmark. So what we did was we took the same images and we said, let's design a quantum-inspired algorithm. We'll run it on a device that is trying to be quantum, and then also run it on a digital device that is simulating quantum, and see how long does it take for us to train, and what is the quality of that trained machine learning algorithm. And what we found is that we take less time and our accuracy is better. And so it tells us that as the real quantum technology improves, we can expect to see faster and more accurate machine learning algorithms come across.
Sridhar, I'd love to hear about an aha or eureka moment that you had during this project.
So what happened was we started looking at when is it that this method finds correct answers when the digital method did not. How come, right? How come the algorithm that got trained on quantum got trained differently on the same data? Because that tells us a little bit about the fact that we're not just solving it faster, it is finding a different answer in some sense, right? A better answer. And so I think that is something that is helpful for us to think about on other projects where we are going to be doing similar comparisons to say, hey, if you're going to figure out if this genetic signature has a predisposition for cancer, and we have a mechanism to do it using an algorithm and digital computer, it has the same issues, false positives, false negatives, etc., etc. And we create a quantum and quantum-inspired algorithms. We want to see, it's going to be faster. Okay, let's do that. Is it going to find better answers? Why is it finding better answers? And hopefully, in a few times, we can start getting an understanding of it's not just getting to the same place faster, it's actually getting to a better place faster.
Wow, so the quantum was not only faster, but did a better job processing the same data and came up with better answers. That's fascinating. What's next for this pneumonia project?
So, for example, here I just created a dichotomy. You have pneumonia or you don't have pneumonia, but you can have different types of pneumonia. So it's a multi-class thing. So the natural next step is to say, if you have pneumonia, which pneumonia? So that is something that's on our books, that we can try to do.
Let's take a break. And when we come back, we'll learn more about other ways Sridhar's work with AI and quantum computing is changing healthcare.
This podcast is brought to you by Carnegie Mellon University. Located in Pittsburgh, Pennsylvania, CMU is a private, international research university, consistently ranked among the top universities in the world. Its trailblazing research is focused on creating, defining, and accelerating the future of artificial intelligence. For more information, please visit ai.cmu.edu.
Welcome back. You're listening to Where What If Becomes What's Next from Carnegie Mellon University. Before the break, we talked about how quantum technology is improving the accessibility and accuracy of diagnosing pneumonia. But what about other diseases?
Yes. So The other project that's healthcare related that I have done both classical and quantum has to do with taking data of people with various types of cancer and their genes and having that matrix of all the various gene markers and the types of cancer. And then to say, can we find out which gene mutations are most likely the cause of this person having this cancer? And this is a very classical cancer genomic problem. And so we wanted to attack this using quantum-inspired computing. So again, we solved it using best-in-class classical methods. We then created quantum-inspired algorithms, and we ran it both on these quantum machines with decompositions and these quantum-inspired, digital machines.
Oh, interesting. So you're actually using 3 different types of tools: the classical computing, a quantum-inspired machine that runs in the cloud, and a full-on real quantum machine. How do the quantum methods compare to the classical ones?
It solves much faster. It also identifies pathways that were not identified by classical methods. So it is actually giving us candidate mutations that were previously not being considered, and therefore can be some new things that biochemists can start learning in their lab to say, oh, I didn't think this combination of genes was going to give it, but what you're telling me is your machine learning algorithm picked up that this could be a very credible source for getting cancer. Oh, I had not even considered studying these gene markers and this combination. And therefore, I never thought about making drugs to worry about these mutations. So I think that's very exciting to us because replicating faster is good. It's a good proof of concept. But the fact that we found some combinations that were previously not found, I think is exciting.
Yes, I think a step closer to a cancer cure would be really exciting. So is quantum the wave of the future? Do you have projects that still rely heavily on what you're calling classical methods?
So I just finished a project where we developed new classical algorithms for liquid biopsy. As you know, that's the holy grail for cancer diagnosis. It is very minimally invasive because you take a drop of blood, and based on the cell-free DNA that is in the blood, that's a signal of various types of cancer. So liquid biopsy, I think, is a very exciting and promising technology. You collect all this information from the blood and so on and so forth, and then you have machine learning algorithms. And people have been studying, what can I do with this data? Can I squeeze out more information from it?
It's pretty remarkable that we're talking about machine learning and AI as classical.
Yeah, I consider it like, it's like my father's Oldsmobile. Undergrad kids know how to do ML and AI. And are people refining things? Are they doing large language models and generative AI that has been hard for the last 2 or 3 years, different from, the old analytical ML? Absolutely.
Let's look even further into the future. There are so many technologies we've covered today, from classical machine learning to quantum-powered machine learning or generative AI. Where is the greatest opportunity or need in healthcare that these technologies can help tackle?
I think the 3 big areas, I think we mentioned it, so let me just say it so that it gets summarized. I think one is early diagnosis, whether you're doing cancer or things like that. How early can you get credible signal? How can you get a credible signal with least amount of data that is accurate to your demographics? I think that is a very important piece, and I think AI, generative AI, quantum, all are going to be helping in that general bucket. The second bucket is, how do we get this kind of access around the world where, they don't have, the best facilities. And so I think the second piece of healthcare that I think is finding low-cost, distributed ways of gathering information that can then provide rapid feedback for, decision making. And I think the third piece goes back to identifying things that people are not thinking about, they're not even finding the answer to the problem because they don't know that's the problem, right? And so I think there are lots of things we don't know that we don't know.
The last question is, what's next for innovation? What do you think is going to be the most important technology in 2025 and beyond?
I think AI is making such tremendous leaps. Generative AI and reasoning and agentic AI and things of that type. I think people are just shocked on how good it is. I mean, it has issues. I mean, it has hallucinations. It finds answers that don't exist. It doesn't know that it doesn't know. I mean, sure. But people are getting better. I mean, they're getting better at putting guardrails. And if you're able to do reasoning, I don't know if you saw the recent example from this DeepSeek. Somebody put in a question that said, which team has won the most number of NFLs, right? And it says, well, let's see. How many teams are there? How many of them have done more than one? And it gives you step-by-step reasoning. And it says, oh, it's the Pittsburgh Steelers and the New England Patriots with 6 each. So suddenly it has gone from, hey, some black box doing some Markov chain, probability thing to giving you reasoning. And then you say, well, I mean, that sounds like a human being reasoning it out, right?
Yeah, sounds like a human talking about football, not a computer. This technology really has found its way into every part of life, from pneumonia and cancer diagnosis to sports talk. That's all for today's episode. Thanks to my guest, Sridhar Tayur, and thanks to you for listening. Please check the show notes where you'll find links to additional resources for this episode. And to learn more or contact us with a story idea or comments, please visit cmu.edu/What's Next podcast. If you are enjoying this show, please rate and review us on your favorite podcast site and share with friends. And be sure to subscribe so you'll never miss an episode. You've been listening to Where What If Becomes What's Next from Carnegie Mellon University, where we are asking the bold questions that become innovations for the betterment of humanity. Stay tuned and stay curious.